Yeah, so thank you, Sharon, for the introduction. So before talking, I'm going to introduce my colleagues and research team. This work wouldn't have been possible without their help. So the agenda for today is that we're going to give a brief description about force sensing resistor in research and industrial applications, and the underlying basis for the piezoresistive and piezocapacitive response in such devices. And then we're gonna give some addressing about the mechanical and electrical setup for gathering sensor data. And we explain an interesting phenomenon we have described, which is the voltage dependency of the sensor resistance, okay? Followed by results and conclusion. So when we deal with force sensing resistor, this technology is like really mature nowadays. Is known in this field as resistive sensor, tactile sensor, pressure sensors. Okay, and it consists on it's fabricated by laminating and insulating polymer matrix between conductive electrodes. This is an application where this sensor has been integrated into a haptic interface for augmented reality. It is also common to find these sensors in industrial application. This is a barrel hand. Okay, although these sensors, these hand fuses are capacitive. Okay, the technology is pretty similar. The fabrication process is similar. Okay, so what is the phenomenon lying behind this piezoresistance? So we have this on-stress polymer matrix, which is sandwiched between metal electrodes, and when you apply force or stress, then the interparticle separation will reduce. Okay, and at the nanoscopic level and microscopic level, we have quantum tunneling occurring between one particle and the other. Okay, and between, of course, the electrodes, and the interparticle separation is reduced. Okay, thus increasing the net current flowing from one electrode to the other. In regard to capacitance, the phenomenon is similar. Okay, but now regarding the general equation for capacitance, now the interparticle separation is reduced, and this yields in an increment in sensor capacitance. So for previous resistant operation, the resistance is typically reduced because the particles are closer, so tunneling conduction is easier. But when dealing with capacitance, actually the capacitance grows with force or with stress. So in order to understand why we have lower hysteresis and lower drift when dealing with capacitance readings, we have to understand the physics behind the phenomenon. This is the resistance, okay, for piece of piezoresistive sample, and as you can see, the interparticle separation affects linearly the resistance and also exponentially, because it's in the argument of the exponential. Conversely, for capacitance readings, it's in the inverse. So if you have hysteresis, this is a plot of hysteresis as a function of the applied stress, then the hysteresis is magnified in resistance values. So if you have a material or you have a sensor, you will always or usually will have higher hysteresis because of the exponential dependency. Okay? So what have we used to read out resistance, and what have we used to measure capacitance? So when dealing with resistance readings, we use this amplifier circuit. Okay, it's a classical circuit when dealing with these sensors. Okay, an important consideration is that the sourcing voltage, okay, must be tied constant all times, because we demonstrate later that the voltage actually modifies the resistance of the sample. And when dealing with capacitance, we must source the circuit with an AC source, okay? And we must use a multiplier in order to decouple the resistance from the capacitance, okay? This is followed by a low-pass filter, okay? And then we can compute capacitance from this formula, okay? A detailed formulation of this is available at this site. So an important consideration is that if you held constant the applied force and just change the voltage, okay, and in this circuit, then you will measure that the resistance is actually voltage dependent. Okay, so this has gone unnoticed in many product data sheets and also in many development of sensors, because usually they assume that the resistance is constant, or I mean it's constant in regard to voltage changes, but it's not. And this, of course, because the toning of resistance is voltage dependent. Okay, we have recently published an article with details on this topic for the toning of resistance and the contact resistance. So in regard to the mechanical setup, we build a custom test bench. It's the author's opinion that these kind of researches should be conducted following, should embrace several sensors, because the distribution of the nanoparticles in the polymer is random. So you may have somewhat different responses in the sensor from one specimen to another. So the study actually embraced 16 sensors. So we have a temperature control chamber, a load cell, and a linear motor for applying control forces. And the results, we first describe what the test signer was. So it embraced loading and unloading force profile and constant step forces for measuring the creep. Okay, so the idea was to measure resistance, well, first to characterize the sensor, and then measure resistance and capacitance, and evaluate comparatively how sensor resistance and capacitive behave under the hysteresis and creep criteria. Okay, so the results. Okay, so the scatter plots 1, 3, 4, and 5. It will be this, and this. They match for conductance or resistance readings. And the rest, which are 2, 6, 7, and 8, they match for capacitance. Okay, in each one of the intervals. So this is the high, medium, and low intervals regarding to the trip error or the creep error. So as you can see, the capacitance always outperforms, okay, the resistance readings, as previously mentioned, because of the exponential dependence on the interparticle separation. So an increment or a given hysteresis in the interparticle separation is magnified because of the exponential. Okay, this is like the underlying basis for larger error in hysteresis and also in creep. Okay, so let's say some conclusions. So resistance is exponentially dependent on the interparticle separation, whereas capacitance is dependent only on the inverse. Okay, this explains the larger amount in hysteresis error. Well, it's the same. These are lower hysteresis and drift errors were measured in sensor capacitance. I didn't say the type of sensor we use. We use commercial sensors because it is easier. They are easily available, and we didn't want to model the effect of manufacturing one sensor from another, because usually you cannot make exact sensors. So you need either to buy them, which are really similar among them, but if you manufacture multiple sensors on your own, unfortunately you cannot make exact sensors. So you were adding an additional variable to your experiment. This is probably a remarkable conclusion. Is resistance is voltage dependent, whereas capacitance is independent of the applied voltage. And finally, well, the usage of capacitance readings is promising towards obtaining more accurate force readings, regardless of in regard to hysteresis and errors. Well, this is the grant support and tech for